So welcome to the lecture. We will continue our discussion about point particle moving in a linearized gravitational field, which is described by a Pierce-Pauli equation. So in the previous lecture, we arrived at a Lorentz covariant equation describing the dynamics of the point particle interacting with this linearized gravitational field, that is the Pierce-Pauli field. And we have shown that only under the following joint transformation of the coordinate and the Pierce-Pauli field, which is given as x mu goes to some x prime mu, which is related to x mu plus lambda. So this capital lambda mu nu provide the fourth set of arbitrary function, and h mu nu x h prime also the h is transformed by this equation, and remember this is a same 4 vector lambda, lower the indices on. So only under this joint transformation, this point particle coupled to this Pauli field, the equation of motion of it remains invariant. So this is a joint gauge transformation of the Pierce-Pauli field as well as the coordinate spacetime coordinate, and all this coupling has to be invariant under these gauge transformations. Hence, the gauge transformation of the Pierce-Pauli field necessitates gauge transformation of the spacetime coordinate as well. So the lesson that we learned is that we have to gauge the spacetime translational symmetry. So you can see that if this would have been some constant 4 vector, it's a translation, usual translation, and Minkowski metric is invariant under such translation. But now it's a function. In fact, it gives a fourth set of function for each of these component, and it becomes a local transformation. So it becomes a gauge transformation. So this is a very important consequence that we learned when we try to couple this point particle with the Pierce-Pauli field. And of course, this can be extended order by order for higher order of h. Note that we are only working in linear ordering h as well as linear ordering this capital lambda, the gauge transformation parameters. But in principle, one can extend it, but we are not going to do that. Instead, what we will do is we will directly write down the non-linear version of it and check that it produces this linearized version. So before that, let's look at one more consequence of coupling this point particle with the linearized gravitational field, and together with what we are going to discuss and what we have done in the previous lecture, they will give us a general principle which gives us the platform to study the full nonlinear equation for the gravity, that is the Einstein field equation, and so on, which we will do in the second half of this course. So we know from Lagrangian mechanics that if the Lagrangian is not an explicit function of time, then there exists a conserved charge which is given by this capital H, which we can construct like this. L is the Lagrangian, and Q is the generalized coordinate, Q dot is the time derivative of it, and P is the corresponding canonical momentum, right? So if this is not explicit function of time, explicit time, then this H is conserved. That means dHdt is 0. So for our case, that is for a point particle coupled with this Pauli field, the Lagrangian that we have derived in the previous lecture, the following. Again, this U is the for velocity. This is the free part, and then there is a term coming due to the Pauli field potential. Right. Now this L is again not explicit function of time. Hence, we can write down this on the quantity H. Right. Here, when we said L is not an explicit function of time, remember we are using the proper time because all these things U is dx alpha d tau. So we are using the proper time to parameterize the world line trajectory of this point mass. So L is not an explicit function of this proper time. So with respect to that, H is conserved, and we can again construct this H by doing this. So x dot alpha and mu is the canonical momentum. Again, we have derived the expression for it in the previous lecture. Okay. Right. And x dot is basically dx alpha deta. Conserved with respect to tau proper time, right? So now let's plug in all these expressions. So x dot we write u alpha, pi alpha we have derived. So let's write it down. And the Lagrangian is minus half u alpha to alpha. Sorry, here let me write it correctly. The second term of m u alpha beta. If you simplify this, it will simply give half m alpha u alpha plus half m u alpha beta h alpha beta. Now, if this capital H is conserved, so we can evaluate it even before the particle entered the gravitational field. It should not matter because it is conserved. It will not change with respect to the proper time. So if you evaluate this H, when H alpha beta is equal to 0, that is the particle is not entered into the gravitational region, then H is basically half m u alpha, and we know that for free point particle, u square is minus c square, which means that this is minus half mc square. But now, as this is conserved, so we are going to equate it with this expression. It is conserved. It doesn't matter when we are evaluating. We are evaluating it at a tau when the point particle is not inside the gravitational region. So it's a free particle. Get this, but this should be equal to this expression. So we get alpha plus right, and let's try to simplify this. So we get the. So I'm just going to write this u alpha u alpha beta contracted with eta alpha beta, right? And then we have beta and so the term c square. So now what is u alpha? U alpha is dx alpha beta. Alpha tau is dx beta tau beta alpha beta plus alpha beta minus c square. Now from this we get by taking the coordinate field and the d tau squared the other side, it beta. Now what is this? So we can identify that this is nothing but the infinitesimal line element between any 2 points on this world line, nothing but d square, the infinitesimal line element or the infinitesimal square line element. Now we can see from here that d square is equal to eta mu nu plus h mu nu, which is a function of x, dx mu, dx nu. And now you can identify that due to the presence of this gravity, which is reflected through h mu nu, the Sphere-Pauli field, the space-time interval d square has changed. It is not just eta mu nu plus eta mu nu plus some h mu nu. It is in general a function of Pauli. So this has now given rise to some arbitrary metric tensor, component of which we will denote as g mu nu, which will be in general function of. So the important lesson is that in presence of gravitational field, that is h mu nu for our case, one cannot demand the Lorentz invariant nature of it, right? Nature be Lorentz invariant. So in presence of this gravitational field, now the metric is not a Minkowski metric. It has become warped, and in general we have to use a generic metric g mu nu, component of which will be a function of. So we are seeing a warpage of space-time. So space-time has become curved, and later we will see that we'll have a non-vanishing component of demand curvature tensor when there is a gravity. So gravity is making the gravity is basically giving you the warpage of test. But you can argue at this point that maybe what we are saying is premature. Remember that we are only working to linear order image. So a priori, there is no reason to believe that this conclusion that we are drawing from this simple exercise, that this in presence of gravity, space-time metric will be warped, rather curved, may be false. but we will argue that indeed the conclusion that we draw in here is correct. So remember that what we have is the following: x goes to x prime, which is related to x by plus lambda mu. Also, the Pierce Pauli field h mu nu goes to some h prime nu x mu nu, which is related to the old field, that is h mu nu at x in this way. Okay. So we have a gauge transformation of both the Pierce Pauli field as well as the coordinate, and this is the same function, this capital lambda, which actually gives you a fourth set of function because it's a 4 vector, and it is generating the gauge transform. And we are working at this point in the linear order in h mu nu, that is in linear order in capital lambda. So now question is that what is the nonlinear completion of this equation? It's not very hard to guess the nonlinear completion of this equation. We are going to write them down and then check that when we linearize it, we will get back this equation. So if we look at the first line, so what will be the nonlinear completion of that? So that will be nothing but a arbitrary coordinate transformation, which we call general coordinate transform. So we go from x to x prime, and this x prime should be some arbitrary function of x. Okay. Here I have suppressed the indices. So if you put the indices, mu goes to some x mu nu. Each of these x mu's will be some function of old x, which are again 4 of x. But this is a arbitrary. And for each of these mu will have arbitrary function. So together you have 4 set of arbitrary functions. This is nothing but the general coordinate transform. Okay. Now remember that we have to now work with the general metric, which we denoted by g mu nu, component of which in general is a function of x. Unlike the Minkowski case, where the components are independent of x, and we know it, they are just either 1, -1, or 0, right? But now, as we have seen, that we have to work with a general metric g mu nu, and just like the Minkowski case, with the help of this metric g mu nu, we can define a notion of distance between two infinitesimally separated points, and the corresponding squared line element is given like this way. This is just a generalization of what we have seen in the context of special relativity using Minkowski method. Okay. Now, if we are going to relabel these two infinitesimal separated points, so one of them at x. So again, I'm not going to write down the Lorentz index of the x, and one of them at x plus dx, and we are now going to relabel them to x prime and x prime dx prime using this general coordinate transformation. But physical distance between 2 points should not change under an arbitrary relabeling of the point. Note that here we are just relabeling the coordinate. So physical distance between 2 points should not change. Then keep this in mind, we get the following. That will give us the following, that g mu nu x dx mu dx mu should be equal to some g prime mu at x prime dx prime mu dx prime. We just say that under arbitrary relabeling, the spacetime physical distance between two spacetime points separated by some infinitesimal distance dx, that remains. From here, it is easy to see that g prime mu at x prime equal to del x alpha x mu del x beta mu g. We just bring this coordinate differential down. And this we'll see is the nonlinear version of this. So together with this arbitrary relabeling, we will now show that this and this equation in the linearized limit will give back these two equations. So let's start from this equation and put the linear transformation on the both sides. Linear transformation means x goes to some x prime, not writing the coordinate explicitly, the coordinate labeling, mu, symbolic, I'm writing symbolically, some lambda, some x. And now you can also have linearized level, g mu nu is equal to eta mu nu plus h mu nu. So it's a small deviation from the Minkowski method, from entries 1 and then some small deviation, right? And of course, g prime mu nu some x mu nu will be again eta mu nu. Eta mu nu is again invariant, we know. Then some h prime mu nu. So let's plug in this linear transformation rule into this and see that we should get back our linear gauge transformations. Then we can conclude that this together with this gives the full nonlinear version of this linear gauge transform, which we call general coordinate transformation. Okay. So let's do that. From this side, we have the following. We have eta mu nu, this side, plus some h prime mu nu, function of x. And what are these actually? So from here you can see that if you use this equation, so x is x prime minus lambda, and then you take this del del x prime. So del del x prime will give a Kronecker delta minus some derivative of this capital lambda, okay? Which will, so this will have del alpha mu minus del prime mu function of x. This second Jacobian will give me delta mu minus, let's say, x, and then again this is replaced by this eta mu eta alpha beta plus h alpha. So at the linear level, so we will again neglect the any product between lambda and h, because lambda is the order of h. So for example, this times this will be order of h square, which we are going to neglect. Okay. So we will have, if we expand this, we will have first term which is this multiply this times this, and then we'll have some term which is this term multiplying this and this term multiplying this. But product of these two terms is basically order lambda square, which you neglect. And similarly, h multiplying these two Kronecker delta, order h, we will keep that. But h multiplying with either of these two is order h square, which again we will neglect. So expand it out and up to order h square, which will get the following: eta mu nu plus h prime mu nu x prime equal to eta mu nu plus h mu nu x minus lambda mu nu x minus lambda mu x. These two terms is basically coming from these two term, this term multiplying this. So for example, if you have this term expanded out, remember that this will be multiplying this, and eta, right? So you can see that beta is contracted with eta alpha beta, so it will be alpha and alpha alpha, and that alpha index is contracted with Kronecker delta, so it will be mu. So it will have delta prime nu capital lambda mu, and similarly mu nu in that the other. So before concluding, let's look at these. What are these terms? One of these terms. So you can have these things, but this derivative with respect to prime coordinate, right? X prime, but x prime is related to x plus capital lambda. So let's rewrite it in the following way. We use the chain rule to make this derivative prime to x derivative. So in the following way, x delta mu prime alpha mu now what is this? So remember, x prime is basically x plus capital lambda. So now let's put the indices both sides, alpha, alpha, and alpha. So we can write it in this way, that x alpha is equal to, because we are working in linear level, I can just take this capital lambda to the other side, and then x alpha x prime mu, sorry, will be, first term will be just Kronecker delta minus so this is again order of h. So the upshot is that this term is nothing but delta or some new Kronecker delta plus some order of h or lambda, whatever it is, lambda. So this is multiplying with some this lambda nu x. So now we can neglect this term because this is order of h square lambda square. So effectively, this term will give you just at the linear order delta mu. Now this is what we need. Remember that here we have eta mu nu h prime mu, we have eta mu nu h, and these two terms. Now we can say that at the linear level, this del prime of capital lambda is nothing but del of capital. That's it. So we have eta mu nu plus h prime mu nu mu nu plus h mu nu x del mu del mu plus order h square term, and if you neglect it, then you have your linearized transformation. So we can conclude that the full nonlinear theory of gravity should be described by a generic curve metric, which we component of which we denote by g mu nu, which is function of x. Generic metric, and the theory must be invariant under the general coordinate transform. Which is nothing but the following, that x we relabel x prime, which is some arbitrary function of x, and g mu nu x, the generic metric, goes to some g prime mu nu x mu, which is related to original metric as this. This is two-factor of Jacobian, and we will actually discuss more of this in the second part when we start talking about differential geometry and so on. But together they form general coordinate transformation, in short, which we'll call ECT. So when you try to couple any matter field with the gravitational field, it should respect this symmetry. That means the equations or laws should be invariant under the general coordinate transform. Equation of motion would remain invariant under GCT. This is the fundamental principle based on which we will try to determine the full nonlinear equation of gravity, and we will see that is the Einstein field equation. So Einstein originally postulate this, and this postulate is known as the principle of general coordinate invariance. And this will form the basis of the studies that we will do in the second part of this. Thank you for listening. We'll end.